Up next, we have a circular motion one. So we have an object rotating in a circle with an acceleration of 7 meters per second squared. That's that centripetal acceleration, or the acceleration of an object going in a circle. And we want to know what the acceleration would be if the radius is doubled without changing the speed. So this is one where we're going to set up our original situation and our new. So in our original situation, we have our equation, centripetal acceleration is v squared over r. So I know that my acceleration is 7. So 7 is going to be equal to v squared divided by the radius of the circle. In my new situation, all right, I don't know my centripetal acceleration, so I'm just going to leave it as an a, and that's going to be equal to v squared divided by 2r, because it tells me that my radius is doubled. Lots of ways of solving this. I think the easy one in this case is to solve both equations for v squared. So we have 7r equals v squared and a times 2r equals v squared. And then we can just set those two equations equal to each other. So we have 7r equals a times 2r. Divide by r to cancel out the r on both sides, and then divide by 2, and I get that my acceleration is 3.5 meters per second squared. Answering to 2 sig figs, don't have to worry about rounding here, it's just 3.5 meters per second squared. We could also think about this logically. If we double that radius, okay, we're doubling something on the bottom of this fraction here, that's going to cut my acceleration in half because the radius and the acceleration are inversely related. Moving on to part B, I'm still going to have my original 7 equals v squared over r, and then I'm going to set up my new one when my speed is doubled. So I'm going to say that my acceleration is 2v, and remember it's that entire quantity squared, not just the v, so 2v squared over r. So that means my new situation is actually 4v squared, because we're squaring both over r. This one, to solve it, I'd actually use a slightly different technique. I'd look at this equation here, and I'm going to factor out a 4 here. So I'm going to say 4 times the quantity v squared over r is my new acceleration. And I see that v squared over r was simply equal to 7, so I can substitute that in. So acceleration is 4 times 7, or 28 meters per second squared. Don't need to round that to 2 sig figs either. And once again, I could do this with logic, thinking about the fact that acceleration is proportional to v squared. So if I double my velocity, my acceleration increases by a factor of 2 squared, or 4. Up next, we have a golf ball being swung in a circle on a string. So there is my string, and the golf ball is going in a circle, something like that. And we want to know when the ball is at the bottom of the circle here, we have the tension, we want to find the speed. So I'm, of course, going to start with my forces acting on the ball in this situation. We have the force of tension going up on the ball, and the force of gravity going down on the ball, and my acceleration, of course, is inward. Setting up my F equals ma in the y direction here, I'm going to have Ft minus Fg equals ma. My tension I know is 17 minus mg. That's going to be equal to m times v squared over r. And that just comes from the fact that centripetal acceleration, when we're moving in a circle, can be found with v squared over r. I substitute in for my mass, which is, be careful here, it's 0.6. I have 600 grams, which is 0.6 kilograms. So 0.6 times 9.8, and that's going to be equal to 0.6 times v squared over my radius, which is 1.6. Whatever the length of this rope is here, that's going to be the radius of my circle. So on that left side, I end up with 11.12, and that's going to be equal to, if I do 0.6 divided by 1.6, it ends up being 0.375 v squared. All right, so solving for v there, I end up getting that the velocity is 5.44 meters per second. Rounding to 2 sig figs is just 5.4. All right, so moving on to this next one, we have a person on a bike going around a curve at 13 meters per second. And we want to know what the coefficient of static friction is going to be between the tires and the ground. So I'm going to go ahead here and set up my forces acting on the bike in this case. So we're going to have the normal force going up, the force of gravity going down, and this is the side view here, so I'm thinking about the bike going around in a circle like that, where that's my center of the circle. So the other force I'm going to have, and the force that keeps it moving in a circle, is going to be the force of friction between the tires and the road. That's what makes it move in a circle in this case. My acceleration, of course, is going to be inwards towards the center of the circle, as it always is, in the direction of that unbalanced force provided by friction. So now I can go ahead and set up max and May. So in the y direction, I have the normal force and the force of gravity, so Fn minus Fg, and that's going to be equal to 0 because it's not accelerating vertically. So that means that my normal force is just going to be equal to mg. I don't know the mass of the bike in this case, so I'm just going to leave that like it is now. In the x direction, we have that force of friction, and that's going to be equal to m times my acceleration for an object moving in a circle, which is v squared over r, right? I always know that's my acceleration when I'm moving in a circle. I can now substitute in for Ff. It's going to be mu s times my normal force. We know that the force of friction is always less than or equal to mu s times my normal force. But I have this line here about the minimum possible coefficient of static friction. So if my mu is as small as possible, that means I need to use all of that frictional force. And so in this case, friction is at a maximum, and Ff just equals mu times my normal force. I can substitute in now for Fn, so mu s times mg equals m, and I know my velocity is 13, so 13 squared over 18. I can go ahead and cancel out the masses here, and I can solve for some of these numbers. So I have mu s times g, which is 9.8, is going to be equal to 13 squared over 18, which is 9.39. And so I can solve for mu, and I get that mu is 0.958. Answering to two sig figs here, that mu is just going to be 0.96. For this next one, we have a car driving up over a hill, and the hill has a radius of 60 meters, so it looks something like that. It's a curved hill, and we have the car there at the top of the hill, so the car is going up and over the hill like that. We want to know the maximum speed the car can have without flying off the hill, flying off the road at the top of the hill. So let's start with our forces acting on the car in this case. We have the force of gravity going down. We also have our normal force going up. We are traveling in a circle here still. It's a little bit different than some of the situations we looked at, but going up and over that curve that is circular does count as traveling in a circle. So we're accelerating towards the center of the circle, which is down. So there's a really, really important line here, this without flying off the road at the top, okay? So what I want you to think about for a second is what actually causes this car to accelerate in a circle while it's going up and over the hill? Well, in order to accelerate, we need that downward net force, which means that gravity must be greater than the normal force in this case, okay, to create that inward acceleration. And as we go faster and faster, okay, that acceleration is going to get bigger and bigger, v squared over r. And so that means that we need more and more force downward, more and more net force down. Well, gravity can't actually change, okay? Gravity is going to be the same. So how do we get more net force downwards? Instead of having a bigger downward force, we have a smaller and smaller normal force, okay? And as we go faster and faster, that normal force keeps getting smaller and smaller and smaller until eventually we have a normal force of 0. And that's the point where the car is going as fast as possible without flying over the road. If it was going faster than that, what would end up happening at the top is the car would be going, it'd be going, it'd be going, and it would just take off and actually leave the surface of the road because there'd be no more normal force and gravity wouldn't be enough to keep it moving in a circle. But there is a perfect speed where there is no normal force, and at the top of the hill, right at this point here, we have only gravity acting on it, keeping it moving in a circle. So that means that we actually only have one force acting on this object. So let's go ahead and set up our F equals ma based off of that. So we have the force of gravity equals our mass times v squared over r. Okay, substituting in for the acceleration of something moving in a circle. I'm going to substitute in mg for the force of gravity, and that means that I don't know my mass here, but they cancel, so I don't have to worry about that. So I can plug in some numbers. I have 9.8 is going to be equal to v squared over 60. So when I go ahead and solve this for v, I get that v is the square root of 588, or 24.2 meters per second. Rounding to 2 sig figs just leaves me with 24. Moving on to our next one, we have a problem about a rock being dropped on the surface of Mars and determining how long it's going to take for that rock to hit the ground. So the first thing that I would do here is I would go ahead and calculate the free fall acceleration on the surface of Mars using our equation for that. So we're going to go ahead and enter the mass and radius of Mars here into that equation. And when we do that, we end up getting a acceleration due to gravity of 3.77 meters per second squared. Once we have that, it's back to kinematics here to determine how long it will take this rock to drop 2 meters. So we know our displacement is negative 2 meters because it's falling. We're dropping it, so our initial velocity is 0, and our acceleration now is going to be negative 3.77 meters per second squared, the free fall acceleration on the surface of Mars. I'm going to go ahead and set up my delta x equation. We know our displacement is negative 2. That initial velocity term just goes away because it's 0. And we have 1/2 times negative 3.77 times t squared. When we go ahead and solve for t, we end up getting an answer of 1.029 seconds. If we're rounding to 2 sig figs, it would ultimately be 1.0 seconds. Moving on to this next one, we have a problem about the International Space Station, which orbits Earth at a height of 200 miles above the surface. And we want to figure out how fast it's traveling and also determine the station's orbital period. So there are two ways of thinking about it. We could think about circular motion, or we could think about satellite motion in Kepler's third law. For this one, I'm going to think about satellite motion in Kepler's third law. First thing I'm going to do, though, is think about the actual orbit of it. So there's the Earth there. We have this International Space Station orbiting around the Earth like that at a height here of 200 miles. So the first thing I'm going to do is I'm actually going to convert that 200 miles into meters. I know that 1 mile is 1,609 meters. And so that 200 mile height above the surface is actually 321,800 meters above the surface. Now that I have that, I'm going to start with Kepler's third law to allow me to find the period of the orbit. So here we have Kepler's third law that allows us to determine the relationship between the period and the radius of orbit. So I'm going to go ahead and plug in the things that I know. I'm solving for that period. So that's going to be 4 pi squared times my orbital radius. So keep in mind, I need to account for the radius of Earth in addition to the height above Earth. This entire distance here, the distance from the center of the Earth to the satellite, is going to be my orbital radius. So for that R value, I'm going to do 6.37 times 10 to the 6th plus that height above the surface. That's going to give me the total distance from the center of the Earth to the satellite, which is going to be the orbital radius. And we're going to cube that, because that's what's in the equation. And then we're going to divide by 6.67 times 10 to the negative 11th times the mass of Earth, 5.98 times 10 to the 24th. Okay? Keep in mind that when you're doing this in your calculator, this entire bottom part needs to be in parentheses. Okay? If it's not in parentheses, you're going to end up getting a wrong answer. So be careful here when you're plugging it into your calculator. So we can go ahead and evaluate this, and we find here that t squared is going to be 2.966 times 10 to the 7th. And then when we go ahead and solve for t by taking the square root, we get that t is going to be 5,446 seconds. So there is our orbital period here for the International Space Station. That actually answers question B, except we have to convert this to minutes. So 60 seconds in 1 minute. And we end up getting an orbital period in minutes of 90.8 minutes. So that answers question B. Rounded to 2 sig figs, it would just be 91 minutes. And now we can use that information to answer question A asking about the station's orbital speed. So in order to find that speed, I'm going to use my velocity equation for an object traveling in a circle here, 2 pi r over t. We know the radius is going to be the same r that we used in the previous part, the radius of Earth plus the height above the surface of Earth. And then we're going to divide by that period in seconds that we just solved for, because we want to get our velocity in meters per second. And so we end up getting a final velocity here of 7,720 meters per second. When we round that to 2 sig figs, it's 7,700 meters per second. All right, moving on to this next problem here, we want to calculate the speed of the Earth as it travels in its almost circular orbit around the Sun. It is actually extremely close to perfectly circular. So what we're going to do is we're going to use our velocity of an object traveling in a circle equation, 2 pi r over t. We know the radius of the orbit, not the radius of Earth itself, but the radius of the orbit is 1.5 times 10 to the 11th meters. Okay, if we think about the Sun here and Earth, that distance between them ends up becoming the radius of the orbit. Okay, so that's why we're using that number. And then we're going to divide by the period. However, we need that period in seconds. So 365 days, we know that 1 day is 24 hours. We know that 1 hour, I'm just going to jump to seconds here, is 3,600 seconds. And so we find that the time for an entire year is 31,536,000 seconds. Okay? So we're going to divide by that period in seconds. And we end up getting the velocity of the Earth as it moves around the Sun as 29,885 meters per second. Rounded to 3 sig figs as it asks, that becomes 29,900 meters per second. For part B, we want to find the centripetal acceleration now, which we know is v squared over r. And so we end up taking that velocity that we just got, 29,885 squared, over the radius of the circular orbit taken by Earth, 1.5 times 10 to the 11th. And we find that our centripetal acceleration comes out to be 0.00595 meters per second squared. And that's already a 3 sig fig, so that's just going to be our final answer there. All right, moving on to our next problem here. We're given some information about one of the moons of Mars, Phobos, that has an orbital period of 7 hours and 39 minutes. And we know that the radius of its orbit is 9.4 times 10 to the 6. We want to calculate the mass of Mars using that information. So we can do this using Kepler's third law. So using that period and orbital radius, we can go ahead and solve for m, and keep in mind in this case that m is the mass of the central object, so that would be the mass of Mars if we're thinking about the orbit of one of its moons. The one thing we do need to do before we go about doing this is we need to get the period, which currently is in hours and minutes, into seconds. So I'm going to go ahead and convert each part of that one at a time. So I'm going to take 7 hours and convert that into seconds. We know that 1 hour is 3,600 seconds, and so that ends up being 25,200 seconds. And then I'm going to take the 39 minutes, 1 minute is 60 seconds, and convert that into seconds as well, so 2,340 seconds. And so the total period in seconds is going to be 27,540 seconds. So I can go ahead and enter some of the information I know here. So 27,540 squared equals 4 pi squared times the orbital radius, which we're told is 9.4 times 10 to the 6th meters. That cubed all over gm. I'm actually going to go ahead and cross multiply here because I ultimately want to solve for this mass. So I'm going to say gm times 27,540 squared equals 4 pi squared times 9.4 times 10 to the 6th cubed. So then when I go ahead and solve for m, my mass is just going to be 4 pi squared times 9.4 times 10 to the 6th cubed all over big G, which is 6.67 times 10 to the negative 11th, times that 27,540 squared. So I just divided by this and by this to get mass all by itself. So I go ahead and work this out, being careful, of course, to use parentheses on the bottom here so I don't screw this up when I enter it in my calculator. And I get that the mass of Mars is going to be 6.48 times 10 to the 23rd. Rounded to 2 sig figs here, that just gives me an answer of 6.5 times 10 to the 23rd kilograms.